So, good morning, everyone. Good morning to all the classes who are watching us. We have already 5 countries here at the EPSC Goes Live for Schools, and that's the 4th event that we do for this conference. So, we are here today with 2 researchers. It's a double talk, so you're going to have double input for the same topic, which is our solar system and its weird cousins. We have here Georgy Makhatadze, who is a doctoral candidate working at the Center for Star and Planet Formation at the University of Copenhagen. Before that, he graduated from the Faculty of Geology of Lomonosov University in Moscow. And he has been engaging in science communication since a lot of years, already 4. He was giving lectures, he has given lectures for Lectures Without Borders, and we welcome him again here. And Rajika Kuruwita is a postdoctoral researcher at the same University of Copenhagen, and she simulates the formation of stars. So that's a combo, right? We need to simulate the formation of both stars and planets to understand what happens there. So Rajika is gonna talk to us about that. She's studying it to determine the dynamical interactions and what is the whole effect of the star formation in the planet formation. And Rajika today has birthday as well. So I wanna wish happy birthday from all of us here. Happy birthday, Rajika.
Thank you.
And yes, the floor is yours. And please, you can start with sharing.
Take it away. Am I frozen? Sorry, did I freeze for a bit?
Don't worry, you can unfreeze whenever you want. We have also here, hello.
No.
From.
Sorry.
Okay.
Okay, I just hope my internet connection is stable. That's the only thing. Okay, so good morning, everyone. So I am Rajika, or Reggie, and we have Georgy here, and we'll be talking to you today about star and planet formation. So you might be wondering why we talk about star and planet formation. Well, as we were just told, you can't really talk about one without talking about the other. Stars and planets are born together in giant clouds of gas. Can you see my cursor? Yes? Okay, giant clouds of gas like this. This is the Carina Nebula, where we have clouds of gas, and then we have dense clumps that sort of start collapsing under gravity. And then as they start collapsing, we have these beautiful jets, and a star and a planet is formed. What Georgy and I will try to cover is I'll try to talk about, this whole picture, what we know, and what we like the current questions and mysteries that we have. So yes, so we'll talk about first our own solar system, because we know a lot about our own solar system almost, and then we'll talk about observations of how stars form and how it fits into our models of our own solar system. And then Georgy will cover evidence from within our solar system, so actual lumps of rock from space, which is pretty cool. And then we'll talk about, other solar systems that we've discovered and how ours any solar system. So let's get started on the next one. So this is our solar system, and you can see that it has these 4. It's not to scale, obviously. We have 4 inner rocky planets, and we have 4 outer giant planets, and then we have some other stuff happening as well. So we've got these asteroid belts here, and another one out here where Pluto and other dwarf planets hang out, and then occasionally we get comets coming in and out. So how did all of this form? Well, let's go on a journey through our own solar system and see what we can figure out. So our solar system has these 4 inner rocky planets. And how do we think they formed? We have this very simple model that I was told. So when we look at how planets form, we see that we have these baby stars with disks around them. So an example is like this. We have a star here, and this red gradient is the gas. And inside the gas, we have dust that kind of grows and sticks together and then builds planets. But we think the reason why we got rocky planets on the inside of the solar system is because the gas is very close to the sun, heated up and evaporated away pretty quickly. So it's kind of like when you open up the oven door and it's on and you get this blast of hot air. That's a similar effect. So this hot air was kind of being blown outwards. And then what's left over is that we kind of get these rocky lumps. So they didn't have time to accrete that much gas. So when you actually look at the Earth, the thickness of the Earth's atmosphere is really, really thin compared to the rest of the Earth. And that's the same on all the other rocky planets. So why don't we go on a quick journey through our own rocky planets. So Mercury has this giant core of ions, about 90% of the size, which this theory helps explain that a lot. All the heavy elements were left behind. We have Venus, which has got the hottest surface. It also spins backwards, which is very interesting. We have Earth, which is the only known planet to host life, unless you consider the recent evidence that maybe there's life on Venus. It also has a moon, that we think formed from a giant impact. And we have Mars, which has the biggest volcano in the solar system, and it also has 2 captured asteroids. So looking at these planets, was there a question? Oh, sorry, I can hear some feedback.
You muted yourself.
So looking at these rocky planets, we can kind of find some similarities and learn some things. So they're all pretty different when you look at them, but they all have craters. So Mercury's got this giant crater up here, Venus got a bunch of craters. The moon even has a lot of craters. And this is very important information because it tells us that these things grew from small things smashing into other bigger things, and it got bigger and bigger. And we actually think a giant collision is why Venus spins backwards. And there's no really way to test that, but it's the best possible theory we have right now. And we also know that the moon and the Earth formed at a giant impact. And we have a lot of evidence for that because we have aged rocks from Earth and the moon. There's like similar ages. And then when the moon is moving away from the Earth, so when you go back in time, they were actually coalesced together. And we're pretty sure a Mars-sized object hit the baby Earth and formed the Earth and the moon system. So those are the inner planets. And what about the outer rocky planets? So we've got Jupiter, Saturn, Uranus, Neptune. How did they form? Well, they actually also fit nicely into our model of how planets formed. I was saying before, the inner solar system, the gas is blown away very quickly, but the gas hangs out in the outer solar system for a long time, which gives the planets more time to actually eat and accrete more gas and become these gas giants that we see today. So let's have a look at the gas planets. So we've got Jupiter, which is the most massive of them. I think it also has the most number of moons. Saturn is the lowest density, and it has the most magnificent ring system. So actually all the giant planets have rings. So Uranus has these rings here. Jupiter and Neptune also have rings, but they're quite faint. So Uranus spins on its side. And then we have Neptune, which also has a ring system. And it's the furthest planet out that we have discovered. There was some evidence a few years ago that maybe there's another Neptune-sized planet very, very far out. And there's been searches for it, but no luck so far. So what have we learned from these planets? Well, again, they're all very different. And we, like this inner solar system, we suspect that it was probably impacts from small things that grew into bigger things and could and made them so big they just created a lot of gas. And so I said Uranus is spinning outside. One of the working theories is, again, a giant collision, which knocked Uranus and is now spinning pretty much at 9 degrees. So this is the correct orientation. So the sun would be way out over here and the Uranus is spinning like that, which is pretty crazy. So these are the planets, but there's a lot more to the planets than just, there's a lot more to the solar system than just the planets. So we covered the inner solar system, which is way in over here and the sun's there. And we've also covered the outer solar system. But there's also the main asteroid belt and all this junk out here, which is called the Kuiper belt. And these places have asteroids. So asteroids are lumps of rock. They can come in different sizes. They can be very small, often kind of lumpy potato shaped, or they can be almost round, borderline dwarf planet. So in these images, they look pretty smooth, but actually with more recent missions where we sent satellites and probes to asteroids, we find that they kind of look more like these rubble piles. So you might have the big asteroid underneath it, but there's all these little bits of rocks and boulders that are loosely bound to the asteroid. And we think asteroids are very important because they're like an intermediate step between going from little grains to becoming planets. And then also in these asteroid belts, we have dwarf planets. So we think if an asteroid gets big enough, it can start to what we call undergo gravitational differentiation. So its gravity is strong enough that it can kind of mold the rock into a ball by heating up its core, and that will send all the heavy elements to the core, and the light elements will float to the top, which is what we see in the rocky planets. So you kind of see this core and crust differentiation. And so, yeah, Pluto is a very famous example of a dwarf planet, but we also have other examples like Makemake and Eris and Ceres. So the only reason they're called dwarf planets, not planets, is because they are not the biggest thing in their orbit. So even though they did make themselves round, there's still a lot of other junk around that they have to clear out. So we also think that comets come from the Kuiper belt, not the asteroid belt. So comets are different from asteroids despite the black and white images. Asteroids are rocky, but comets are icy. And this is an important differentiation. We think that comets might have been very handy for delivering ice into the inner solar system and maybe to Earth. So we think that short period comets like Halley's Comet potentially come from the Kuiper belt, which is just outside Neptune. But then long period comets, which take thousands of years. So like the Neowise comet that came around this year, we think that they originate from this hypothetical region called the Oort cloud. Hasn't been confirmed, but when you look at these long period comets, they seem to sort of cluster out here in this Oort cloud.
Dear Rajika,
someone?
Dear Raji, sorry, just sorry to interrupt you. We have a lot of time, so if you could go a little bit slower for some of the classes that translate real time, we have time. Don't worry at all.
Sorry.
No, that's great. That's great so far.
Okay.
So I stopped you. Sorry, at the point you were saying about this year's comet, the one we mostly saw in the summer in the upper hemisphere, northern hemisphere.
Yes.
There was from this Oort cloud, right? So sorry there.
Yes, so we think those long comets, that one has a period of 6,000 years, I think. So the next time it'll come around is 6,000 years into the future. So those really long period comets, we think that they came from this Oort cloud. Let me just click ahead. Yes. So that's our solar system and all the various parts in it. So let's just continue on. So what do observations of star formation say about our model? So does our model make sense when we look at young solar systems in the universe? So what we see here, we have these clumps of gas, as I said, and they start collapsing and they form a young star. So we've seen some of these clumps in higher resolution, so you don't have to think about this too much. Just these very white blobs are where we think baby stars will form, just because the gas is really, really packed in there. You might also notice that stars seem to form together in clumps, in families of groups. We'll ignore that for now, but that's actually very important for my own research. So what happens after you get these clumps of gas? Let's go into that. So you have this little clump of gas like this, and then it's actually spinning very slowly. But as gravity kind of starts pulling it in, it starts to spin faster. This is due to what we call the conservation of angular momentum. Angular momentum is hard to think about, but a good demonstration is this ice skater. So when she had her arms out, she was spinning slowly, but when she brings them close in, she starts spinning faster. So her arms and legs are further out, and she brings them in and starts to spin faster. So the same thing is happening to this cloud of gas. It was spinning slowly, but as it starts to collapse, it's spinning very, very fast. And things that spin very fast tend to want to kind of flatten out and make a disc, like this person spinning this dough into a pizza. Because he's spinning it so fast, it just sort of stays out in a disc. So the same thing happens in space. We have this baby star in the middle and this disc around it. And then there was a few other stages involved. So it's okay if you don't understand this. I only started to understand it in my master's, but there are magnetic fields in the universe, and magnetic fields are very important. And they actually launch these giant jets, which are important for taking away angular momentum, because if the disk is spinning too fast, it doesn't want to collapse anymore, and that can actually stop the star from forming. So we need to get rid of some of that energy, and that's what these jets are for. And we have observed these jets. So these little lobes are jets from young stars at various stages. This is a very early stage where the jet's just been launched, and this is a star where they're pretty young. There's only very small lobes, and then we have these bigger jets here. And we also saw them in the previous image of the nebula. I pointed out some jets. And there are good ways to kind of look for where stars are being born. So then we could start observing disks where planets will form. So the first disks that we saw were in the Orion Nebula here, and we could see the shadows of disks forming. So Orion Nebula has all these very bright stars, and they were kind of casting these shadows on disks. And we actually think some of the light from these stars was so strong that it was actually blowing away some of these disks. So you might see that this one is actually over here, and it has these stars up in this direction. Is blowing this disk into a tadpole shape. So we could see that these disks were around baby stars, and that was good because we think that we needed them to make planets. But these disks are actually very, very big. They're about 8 times bigger than our own solar system. So you might ask the question, did our own solar system look like that? Well, we're not very sure. But in the recent decades, we started to build much better telescopes, and we could see on even smaller scales more disks around young stars. So one of the first images to come out was this one called HL Tau. And this was 5 years ago now. It was very exciting to see this because it was like the first time we were seeing a protoplanetary disk, that's where planets form, at this resolution. So there's a star in the middle here, just at the wavelength that we're looking at. It's all blurred up. But we saw this, and we saw these gaps, and we were thinking like, could there be planets in those gaps that are carving it out? It was very exciting. So this was the first sort of high resolution protoplanetary disk that we saw. But then since then, we've been able to see a lot more, and they have different properties. So some of them have very thin rings, some of them have very thick like gaps or multiple rings. Some of them have sort of asymmetries. There's a clump of dust or something on that side. Some of them have like spirals, like a spiral there. This one has a very faint spiral. You even have multiple stars. And sometimes they're very like compact disks, or sometimes they're very spread out. So yes, we are starting to see these baby like disks where planets will form, but how do we get from the dust that is in planets to in disks to planets? So this is where Georgy will take over.
Yeah. Hello, everybody. And yeah, so now let's dig into some very, very deep details about how planet formation is going on. And so the big question is that first we have interstellar dust or circumstellar dust. So on the left picture, you can see different, so those are photographs from the electron microscope of stardust grains. And those grains are like in the range of sizes of 1-2 micrometers, but those are the biggest ones. there are a lot of grains which are way smaller and which we are still not really able to make a picture of it. And so how do we get from 1 micrometer to planets with a size of, I don't know, something like 1,000 kilometers, something like that? So what's going on in between? What processes make this happen? We know that asteroids are somewhere in between those, but we don't really know how processes are going. And so on the next slide, Rajika, Reggie, next slide. Yeah, thanks. Yeah, on the next slide, here we see like a scheme of what can happen if two particles collide in space. And when the particles are of the size of the dust, something like micrometer, 2 micrometers, millimeter even sometimes. So those particles easily stick to each other. And when the particles stick, they stay together, and that's how we grow things in space. But when the particles reach the size of about more than millimeter, and so around 1 centimeter or something like that, they start to bounce from each other. And so this is called 1 millimeter bottleneck or 1 centimeter bottleneck. So at this particular size, anything that collides in space is usually bounces from each other, and it's really, really hard to to grow things beyond this point. And right now we don't really know how exactly that happens. And so the main model right now, the main theory right now is that we need in the protoplanetary disk, we need somehow aerodynamically concentrate so many of those particles that it doesn't really matter what they do to each other. They will stay together just because of that so many of them that they start to gravitationally attract to each other even before they collide. But, and this is how, yeah, on the next slide. And this is how we get what is now asteroids. So nowadays asteroids are leftovers of back then old days planetesimals, and those are basically baby planets, something like precursors to how from what we form planets. So we get somehow, we don't really know, but somehow aerodynamically we concentrate a lot of particles and we make planetesimals, or what is now leftovers of what are now asteroids. And how do we make planets from planetesimals? And there are two main ways to do that. First one on the upper picture is collisions. If we collide two big asteroids, usually we will get a bigger asteroid, and if we collide enough of them, we will get a planet at some point. And we have some evidence that this happened. And another process that can happen is called pebble accretion. Pebbles are particles of the size of around 1 centimeter. And we already know that there is a bottleneck. So it's really hard to make something bigger than 1 centimeter. And that means that we're going to have a lot of particles of the size of centimeter. If we are efficient about producing particles of the size centimeter, 1 centimeter, but we are not inefficient about producing anything bigger, then we're going to have a lot of particles of that size. And so pebble accretion of those particles, which we are very efficient about producing, if we have one big planetary embryo of a size of already bigger than typical planetesimal, something we can call protoplanet, pebbles can accrete on those planetary cores really, really fast. And that's another way to make planets. And the main difference between those two processes is the main difference. Of course, those two processes are completely different, but in the outcome, the main difference is that pebble accretion is way faster. And on the next slide, we can see. And on the next slide, we can see. But to test how exactly planet formation going on, we need to find some evidence. And apart from observations and modeling, we have another third way of obtaining evidence about planet formation. Those are meteorites. If we meteorites are again leftovers of planetary building blocks. Of planetary building blocks. And in the beginning, to clear up all the terms, there are many confusing terms about meteorites, and so we have three main ones. First one is meteoroid. Meteoroid is a small rock that flies in space. Meteor is a small rock that flies in the atmosphere, and meteorite is a small rock that already landed on the surface. And so that's basically all the difference. And to be completely accurate, meteors are not even the rocks themselves, but the atmospherical feature when there is a lot of light and there is like a falling star. But yeah, so we study meteorites. I study meteorites to get some evidence of what exactly and how exactly it happened. Yeah, next slide, please. Yeah, so meteorite, where do meteorites come from? Where do we have those leftovers in the solar system? And there is, for that we have two main places. We have between orbits of Mars and Jupiter. So on the scheme, on the right side of the screen, you have a scheme, and in the top left you have the close up into the solar system. So in the inner part we have Sun, all the terrestrial rocky planets. Then we have a cloud of yellow dots. Those are main asteroid belt with a lot of asteroids, and around that we have Jupiter. So yeah, most of the meteorites come from this main asteroid belt. And then if we go further out, we see that in the very center we have Jupiter's orbit, and then we have orbits of other giant planets, and then we have a cloud of scarce blue dots. This is Kuiper belt. This is another region with a lot of asteroid-like bodies, and we are not sure we get any meteorites from there, but we hope we do, and we try to study them as well. But yeah, those are really way harder to sample from the Earth because the Earth is far away from that. So on the next slide, what we can see on the next slide. Yeah. In order to study the planet formation, we need to understand what types of meteorites there are. And there are two main types. And one of them is primitive meteorites, and the other one is differentiated meteorites. And let's start with differentiated because it's a bit easier to explain that way. Can we go next slide? So those are differentiated meteorites. They can be described as stony meteorites, iron meteorites, or stony iron meteorites. And again, to be accurate, this is not a strict classification because primitive meteorites can be stony meteorites usually. So, but here it's easy to describe differentiated meteorites as those. And so, and what's going on with differentiated meteorites? What is that? Differentiated means that those meteorites come from celestial bodies that gone through differentiation. And differentiation is a process when one single planetary body divides into different parts. And it's usually a metal core and rocky mantle and rocky crust. And so iron meteorites usually represent cores of big asteroids or small planets. And stony meteorites represent mantles and crust of those planets. And nobody actually knows what exactly is going on with stony iron meteorites. There is a hypothesis that they come from the boundary between the metal core and stony rocky mantle, but this model doesn't really work very well, and nobody actually knows what happens to those meteorites, where do they come from. So if we want to study planet formation, something that happened before planet, differentiated meteorites are not going to do really well because those meteorites are already, something happened to them after planet formation. So we first formed the planet and then this planet differentiated. So we need primitive meteorites, and primitive meteorites are literally leftovers of planetary building materials. And primitive meteorites are called chondrites, and they called chondrites because most of them contain, next one, please. Yeah, because they called chondrites because most of them contain chondrules. And chondrules are those round grains. And yeah, we have a lot of school from Greece. I guess you know what that means. So yeah, that comes from chondrule, from Greek, means something like grain. Please correct me if I'm wrong.
It's correct. It's correct.
Yeah, and so those grains, they all very circular, and they all of a size about 1 millimeter, 1 centimeter. And how do chondrules form? Yes, chondrules, they are droplets of melted material in the protoplanetary disk. So if we have a clump of dust, and then yeah, we stay here for now. Yeah, if we have a clump of dust, and this clump of dust for some reason becomes too hot, and nobody yet knows this reason. This is one of the bigger problems in meteorites, because nobody knows what exactly makes chondrules form. We know that somebody heated it somehow, and then we understand what's going on. So when the dust hits, it melts, and then we have a droplet of liquid silicates flying in space, and this then solidifies, and we have a solidified droplet. And we in the solar system, there are a lot of those chondrules. They are literally everywhere in most of the primitive meteorites, and we think that those chondrules are those pebbles that later accreted on planets. And the second part of primitive meteorites, which is very important to know about, are refractory inclusions. So here, the red, those are refractory inclusions, and that means that they are composed of material which is not only really hard to melt, but also really hard to heat up, but to evaporate. But from their structure and how they're composed, we know for sure that they are a product of condensation from gas. And so we have something composed of very, very, very refractory material, which is near to impossible to evaporate. And then we have gas of this composition condensed into those inclusions. And they are believed to form very close to the sun in the first tens of thousands of years of its existence. Yeah, so on the next slide, we should see, yeah, so on the next slide, I can explain how we can test it. So studying meteorites is very useful, not only because we can find some evidence of how planet forms, but also because we can get ages of a lot of events very, very precisely. And how this happens? This works because we need radioactive decay for that. For example, if we have a sample where there is some uranium, we're going to have, for example, this 235 uranium in the sample. I mean, we're going to have both, but let's talk about one of them for simplicity. The other uranium I'm talking about is 238 uranium. And so those are two isotopes of uranium, and they are different in terms of how exactly they decay, how quickly they decay. And this one, 235, is the one we use to make all the energy, all the bombs, all good and terrible stuff about uranium. It's from this isotope. So yeah, so if we have uranium, with time, it will decay into lead. And there are two main features of this decay. First one is that for single atom of single nucleus of uranium, we're going to get single nucleus of lead. And second one is that this decay is going to depend on time with very understandable law. So if we have a meteorite and we can measure its chemical composition and get exact, and we know about this meteorite, how much uranium it has, how much lead it has, then we can just calculate how much time have passed since the last time this meteorite was in chemical reaction. Because before that, all the uranium and lead were homogenized. And so if we have any meteorite with those two elements, we can measure its composition and tell the age of that meteorite, and the age would be the last time there were any chemical reactions happening. And so on the next slide, we have a summary of the data we got, like we, humanity, not me personally, of the data we have about using those dating. So here on the bottom, we have on x-axis, we have on the left 4 billion years, 567 million years. This is about the age of the solar system, and then to the right we have younger and younger ages. So those are in million years, and we see that. So on the top half with gray shading, we see interpretation and processes that happened in the solar system, and on the bottom half we see which meteorites, which actual pieces of rock are responsible for the processes we interpret them. And so on the bottom we have a short red area, which is called CEI, condensation and melting. And CEIs are calcium aluminum inclusions. Those refractory inclusions, yeah, they also called calcium aluminum inclusions. And so this is the short period of time when those refractory inclusions were forming. And this corresponds to a period when the sun have just formed. We can get high enough temperatures for those inclusions to form only in the very beginning and very beginning of the sun's existence and very close to the sun only. And then we have long period of about 3 million years, which is blue here on the presentation. Those are period when we have conjules. So we have conjules, and this is interpreted as the period when the protoplanetary disk existed. Because to form conjules, we need a lot of dust everywhere, and so yeah. So we interpret that during this period we have conjules, and during this period we have a lot of protoplanetary disk, and that means that during this period most of the planet formation happened. Because if we accrete pebbles, which can happen that fast, because pebble accretion can form planet this fast. Yeah, and on the next slide, we're going to see a bit of additional evidence on how the solar system is structured. So here we can see isotope anomalies for titanium and chromium, and so those are two chemical elements, and in this context doesn't really matter which chemical elements we're talking about. Here we're talking about isotope anomalies, and isotope anomalies are differences in isotope composition of this one specific element. So the isotopes are varieties of the same chemical element, but different in terms of its nuclear composition. We can have a bit heavier or a bit lighter nuclei, and but they're going to be the same chemically speaking. And so isotope anomalies are differences in this composition, which are formed not because of chemistry, not because of chemical reactions. Those anomalies are formed because those materials are formed from different material initially. So here we can see that basically on the lower left half, we have Earth, Moon, Mars, and a bunch of meteorites of one composition, which is significantly different from the composition of carbonaceous chondrites on the top right. And carbonaceous chondrites are chondrites which, so they called carbonaceous because they contain a lot of carbon, not really that much, but more carbon than any other meteorites. And they contain, in general, way more different elements, different volatile elements like hydrogen and all those elements, light gaseous elements. And basically, it is believed that carbonaceous chondrites come from further into the solar system. They come from, if we have in the inner solar system, we have rocky planets where there are no gases. Then in the outer solar system, we have more gases and we have giant planets. So those meteorites come from further in the solar system. And so this diagram means that we have that rocky planets and gaseous planets formed from completely different material, which was from significantly different material, which was almost not mixing between each other. Because if we had interaction between those two parts, then it means then we would have had some compositions in between those. And this is interpreted as early formation of Jupiter. Because Jupiter is the biggest planet we have. It's a giant gas planet. And if this Jupiter forms early enough, it can make a gap in the protoplanetary disk. One of the gaps Rajika showed you before in the images of protoplanetary disk. And if this gap is wide enough, it can make mixing of different parts of this solar system, make mixing of them very difficult. Yes, and on the next slide, we're gonna see a bit of we're gonna see an evidence for why we believe that the moon formed via giant impact. And so here we again see isotope composition of different bodies. And so the line called TFL, this is terrestrial fractionation line. This is the line where all terrestrial compositions, or anything you pick up on the Earth, apart from meteorites, anything you pick up on the Earth will be on this line. And for example, on the top we see another line formed by Mars. So those are meteorites from Mars, and they have another line. And in the bottom we have kind of extended cloud, because those are HED, those are meteorites coming from asteroid Vesta. So basically here we see that all the different bodies in the solar system have different oxygen isotope composition, and they all have their own lines on this diagram. But if we have yeah, so and then we see that the moon and the Earth, they have literally the same composition. All the lunar meteorites, they come on the same line as the Earth, and this is sometimes interpreted as happened because we had so high temperatures when the giant impact happened that basically all the material between Earth and Moon became equilibrated and became it was mixed. It was well mixed when the giant impact happened, and that's why it's all indistinguishable right now. Yes, and so now Rajika is probably going to talk about what we have other than solar system, right? Is it?
Yes. Sorry, just to help keep the people with us, now that we finished the part of Georgy, you said giant impact. You meant that there was a giant impact between the moon and Earth, and then they crashed, and then they came back again. and now they stay where they are.
Impact was between proto-Earth and some other planet.
From which came the moon?
Yeah,
like,
from which came the moon. So
okay, so like that's when we say giant impact.
But the thing is that this impact was hot enough that material became so the material became homogenized.
Okay, thank you. That's just because not everyone has heard before about the giant impact for the Earth and the Moon, and the proto-Earth and proto-Moon. So sorry.
An interesting piece of trivia for that impact, we call the object that hit the proto-Earth Theia, because that was the mother of the moon in Greek mythology, I believe.
Now I have to look this up.
Okay, yeah. So we call it the Theia impact because that was the mother of the moon and the moon came out of it, Anyway, I will continue on. So Georgy just told us about what evidence we have for planet formation in our own solar system. And now I'll talk about other solar systems that we've discovered and how they compare to ours. So there's a few different methods that we have developed in the last 30 years or so to find planets around other stars. I'll just only go through a handful because there is a lot. The method that's found the most number of planets is what we call the transit method. So this is the transit of Venus back in 2012. And this is just showing how much light was coming from the sun. And you see that when Venus was going in front of the sun, the amount of light dropped. It actually dropped a very, very tiny amount, so less than 1%. But we have telescopes like the Kepler telescope and the TESS telescope, and they're just looking at stars all the time to look for these little dips in the light. And with this method, we have discovered around 4,000 planets, and it's been a really handy method. But the only problem with this technique is that the planet has to pass in front of the sun from our perspective. But if that system is not in the quite right orientation, it might be a bit off, and then we wouldn't see these transits anymore. So we have to find some other methods. So we do have some. The next one that's found the most number, the methods found the next most amount of planets is the radial velocity method. So this is not to scale again, but this is where we look at the kind of the shift in the light as a planet or something else goes around the star. So you have a star and you have this planet here, and the planet is actually tugging on the star. So if this happens in our own solar system as well, between Jupiter and the sun. So if there was aliens looking at our own solar system, they would see the sun kind of doing this wobble at, I think it's 5 kilometers a second, and that's caused by Jupiter. And we can see this in other stars. So if we just keep looking at a star and we look at the spectra of it, the light of the star kind of gets bluer and redder because of the Doppler method, Doppler shift. You might have heard it before. A common example of the Doppler shift, it happens in sound as well, is if you hear like an ambulance or a siren as it's driving towards you, it's got a high pitch, so like wee-oo, 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 wee-oo. Sorry. And then when it's driving away from you, that pitch drops, it becomes longer. So wee-oo, wee-oo, wee-oo. So that is the Doppler shift. That happens in sound and it happens in light as well. So as the star is coming towards us, its spectrum becomes bluer, and then as it's moving away from us, it becomes redder.
So sorry, the ambulance is the star in this case?
Yes, the ambulance is the star in this case. Yeah. So we see that in stars as well, and we have discovered a few planets like this. And this doesn't require the planet to be passing in front of the star from our perspective. But these are all these are indirect methods, kind of. Well, transit method's pretty direct, but the radial velocity one is indirect. The best way to find planets is probably direct imaging, but it's definitely the hardest. So this is a direct imaging of some planets. There's 4 planets going around this star, and we have to use a coronagraph. So it's just this little thing that we use to block out the starlight because the star is super bright, and the planets don't produce their own light. Planets are reflecting the light from their star unless they're very, very young. So we haven't discovered many planets with this method, but it's the only way that we're certain that what we're looking at is a planet. So this is one of the most famous examples. So you can see if we image it enough, we can see these planets go around. But this takes many, many years because so our Earth, well, obviously has a period of 1 year, but then if you want to look for Jupiter's or Saturn's, and you've got to be looking for like 5 to 10 years to even just see these shifts. So it's a very difficult method. So now that we've discovered a lot of planets, thousands, I think the number's almost 6,000 planets around stars other than our sun, what do they look like? Do they look anything like our own solar system? Well, actually, no, they're kind of weird. So the first exoplanet that we discovered, it was actually the year that I was born, 1992, was around what we call a pulsar. So a pulsar is a dead star. And we found that there was, the pulsar has this beam, and we can see that the beam was rotating, but there was also a little anomaly to it, and that was caused by a planet. And that was really crazy because to make a pulsar, it has to explode. It's a dead star that had undergone a supernova. So astronomers were like, this is really weird. Did this planet survive the supernova? Was it made after the supernova? So that was really strange. The first planet was around a dead star. But then we started to find planets around what we call living stars, main sequence stars. And with when you're searching for anything, it's easiest to find the biggest things first. So it's like if you're driving, if you're driving through a mountain range, you see the biggest mountain out in the distance first before you see like the small rolling hills closer to you. So the same thing was happening with observations. We'll find these gigantic planets, we call them hot Jupiters, that were very close to their star. And that was crazy because with our own model, we were saying that the giant gas planets should form further out and should just hang out there like Jupiter and Saturn. But we'll find these hot Jupiters that were bigger than Jupiter, closer to their sun than Mercury. So we weren't sure how they were made. We think that they might have been formed further out and they migrated inwards, or maybe they were formed close to the star. We don't know. These are still open questions that we have. This is one of my personal favorites. We found planets around multiple stars. So we only have one sun, but there's actually a lot of stars in the sky that are more than one sun. So you have binaries where you have 2 stars, or triple stars, or quadruple stars. And we found planets around them. So a popular example is Tatooine from Star Wars, if anyone's watched Star Wars. Also Gallifrey from Doctor Who, and Margaret Thayer from Hitchhiker's Guide to the Galaxy. So science fiction has for a long time thought about planets around multiple stars, and we have started to discover planets around multiple stars. So that's pretty cool. We don't know a lot about how they form or whether it's easier or harder to make planets around multiple stars. So these are some of the questions that I like to think about. And then we've also found some just other peculiar systems. So there was the TRAPPIST-1 system that was discovered a few years ago. And it's this very, very compact system. The sun, like the TRAPPIST-1 sun, is very small. It's about 1/10 the size of our sun. And it has these 7 planets, which are all very, very close to the sun and orbiting it very quickly. So the whole TRAPPIST-1 system fits within the inner orbit of Mercury. So we're finding these very compact old systems. So we don't quite know how they formed a long time ago because there wasn't as many metals in the universe, and just how they've survived.
That's fascinating. Let me just let me pause here just a second, Rajika. We can maybe go on for a couple of more minutes to not lose the attention of the students, because it's a lot of material that they have already a lot of questions about.
Yeah.
So for that, for the TRAPPIST system, I would like to note what you just said. To make sure everyone is on the same page. So we would have something like 7 planets orbiting within, like closer than Mercury. So our closer is Mercury, and it would be 7 planets fitting in between.
Yeah.
Almost close to the star, right? I mean, not touching the star, I would say, but like really.
Very close. Well, I remember the star of the TRAPPIST system is much smaller than our sun as well. So
okay, it's not that strong. It's not that hot, right?
Yeah. So it's very small.
But yes, please go. Sorry, another
okay.
2 minutes, 3, and then we can go on with the first questions. Thank you.
Yeah. So that's pretty much all we have to talk about here. But we do have a few extra slides to talk about our our own research. So I'll quickly go over my research, and then Georgy will go over his, and then we'll take questions. So as I was saying, my research, I like to think about these multiple stars. So I showed this slide before where we have these kind of baby clumps that will form stars. A lot of stars are formed in, families. And this plot is scary. Don't worry. The only thing you have to think about is this red line, which shows that massive stars very much are very likely to have like another star around them, and small stars are less likely, but they still have multiples. So stars like our sun over here, about 60% of stars like our sun have another star around it. So then I think about how they're formed and how we can make planets around them. So yeah, we've discovered planets with multiple stars. And when astronomers have thought about planet formation, so the model I showed before, we've often only thought about having one sun. But like I said, a lot of the stars in the sky are in 2 or 3 systems. So you have lots of suns around. So how does that affect planet formation? So I like to run simulations. So this is just a quick video of one of my simulations. This is all gas and magnetic fields. And we have these 2 stars here, and they are interacting with them. And we have these bursts of accretion. And like I said, planets form in disks. So these stars had their own disks, but while they're interacting, they're destroying these disks, which is, you're like, how do you make planets around them if the disks are being destroyed? But as the system evolves, you actually get this very big circumbinary disk where that looks pretty stable and looks like there's a lot of material there, and maybe planets could form in a system like that. So
yes, actually, Rajika, that's exactly one of the questions. Maybe since you are on the video, you can go a little bit back and we can answer, I think, immediately. This question comes from a school in Turkey. No, it's a school in Greece, sorry. This was about the multiple stars. So you just told us, you just showed us this colorful plot and the 2 shiny dots orbiting each other, right? So it's 2 stars, which means they're both orbiting around each other. It's a complex thing. Can you tell us about these colors? Why the colors are different? What does this mean for planets?
Okay, so this is hard to interpret. So where the white is, that's just where there's more gas, and these are just showing where the stars are. And typically where you have more gas, then you'll have more dust and then more likely form planets. So this system has like its own disk here and own disk here, but while they're interacting, those disks are being destroyed. So you can see that this disk is being stripped off and all the gas is moving outwards. So I don't show it here. Yeah, I guess at the end of the simulation. Yeah, so kind of like this, we have this dead zone in between, so there's no gas here, but we do have a lot of gas out here, which is a good sign, because then that could mean that there's more dust and more likelihood of forming planets. I hope that.
Okay, so what you say is that if the planet doesn't form within the time this gas part is preserving, then it doesn't have time to form. We have it breaks, possibly doesn't grow enough, as Georgy told us.
Yeah,
and then we have to follow what happens. We have to follow each stream, right?
Yes, pretty much. Yeah. So this is one of the questions that we're trying to answer. Is how do you make these planets? Because when we think about how not just 2 stars, but 3 and 4 stars, when they're all forming together, they have these complex dynamics that just want to destroy the systems. And we find planets in systems like that. So we don't know how they happen. So I'll continue on to Georgy's research. Sorry.
Yes. Hello again, everybody. And I recently started working on my PhD project, something about half a year ago, more than half a year ago. Yes, and I'm just gonna briefly explain why I do what I do. And I study, so we talked about isotope anomalies in different meteorites and how they can be useful to trace different processes happening in the solar system. And for that, I'm going to study isotopes of iron and nickel, just because those are very, very abundant elements and there are a lot of them everywhere. And I'm going to study those isotope anomalies in those elements in iron meteorites. And the idea is that, of course, we're going to have a problem. Of course, I'm going to be limited in my study because if I want to study something before planets, I need to study meteorites that formed before planets. And iron meteorites are not that primitive. They formed later. So I'm going to limit it on that respect. But iron meteorites are, as you can probably guess, way harder and way more durable. They're not technically harder, they're way more durable than all the stone meteorites. And that gives us a chance that we're going to sample a way larger part of the solar system with those meteorites if we study them. So the idea is that I will be trying to reach further into the solar system and see what's going on beyond what we have studied so far. And yeah, basically that's what I was going to tell. Thank you very much. And,
we thank you. Thank you both, Rajika and Georgy. And I will go on without losing time to the questions because the schools are waiting, right? So we answered about the multiple stars. It's already complex. Let's see on the stars, staying on the star topic. There's a question from Turkey, from a school in Turkey, asking if the other suns are similar to our sun, and if not, do you have any clues from these materials? These other stars materials.
Okay, so we know that there are different types of suns, if that's what you're asking. So yes, we see that there are stars like our sun, which is pretty average, but actually smaller stars are even more common. So stars that are dim and red. So if we go back to the TRAPPIST system, can I escape from here and go back here? So the TRAPPIST system, this type of star is actually one of the most common types of stars in the universe. And that's why this program was made, because if you're trying to look for planets, you probably want to look around the most common type of star, which is these small red stars. And we're just wondering whether you could make planets around these very, very small stars. So we are discovering them, but they're very faint, so it's hard to see them, but there's a lot of them in the universe. And we also know there's lots of very big stars. So like giant stars like Betelgeuse, if you look up in the sky. And we're not sure if planets form around those ones either, because very, very big stars, they have short lifetimes. They kind of eat all their fuel and explode in a supernova. So they only live for a few million years. And Georgy was showing before that the timeline for making the solar system, at least for making our own solar system, was at least, 5 million years or so. So if you have a big star and it only lives for like a couple of million years and explodes, like, is there time to make planets around them? So there's different types of stars, and we're also learning about how we can make planets around them. Yeah, I hope that answers the question.
Also, as I understand, the question asks about the same stuff, but also from the point of view of studying dust. And for this, I can say that studying pre-solar dust in meteorites it can tell us a lot about what was going around solar system and what was going on in the solar system, what happened to this dust in the solar system. But in terms of general picture of what stars are there, it's really not very informative, because most of the dust, the dust is it's more than 4.5 billion years old, so it's really long time, and it's really hard for dust to survive. And the thing is, most of the dust we have comes from very specific types of stars. Those are asymptotic giant stars, preferably around 2 solar masses. And this is because those stars are very good at producing very, very refractory and very, very hard to destroy dust. They have a lot of carbon, and this allows them to make something like silicon carbide, which is really hard to destroy. And a lot of other stars produce also a lot of dust, but this dust is really easy to be reprocessed into another thing, which will not be recognizable as a pre-solar dust. So, I mean, we have a lot of dust from those giant stars, but that's because those giant stars are good at producing durable dust, not because there are a lot of those stars.
So wait, what you're saying is that even if we have a small star like the one at the TRAPPIST system, which is another sun, right? It's another type of sun. Yeah. We would still have dust coming from the activity of other stars?
Yes. So outside. So I was showing before, like the Orion system. Let's go view. There's big stars and small stars here, and it's all very compact. So actually in the time scale that this small star might make its planets, these big stars might go supernova and blow its guts into this system. And that's what Georgy is seeing, right?
We're not yet. Everybody looks for an evidence of supernova explosion right at near to baby sun, and nobody can find it. But yeah, like that's what we are doing here. Yeah, we're looking for that as well.
Okay, and there is a question for Georgy, which is, what will be the impact of a huge meteorite if it collides with Earth? Sustainable.
Yeah, it depends on the size, but like in general, I sincerely don't know how big it should be to cause instant significant damage. Something like tsunamis or like huge craters, but even a relatively small meteorite is going to be enough to cause significant disruptions in the climate cycle. If the meteorite falls, then we're going to have a lot of dust everywhere, and this dust is going to block the sun for several years. So this is basically the same as 2012. The volcano Eyjafjallajökull in Iceland erupted, and we had a lot of dust everywhere, and we had air transportation blocked, and we had a bit colder summer afterwards, things like that. This is going to be the first and most obvious, not the first in time, but this is going to be the most obvious result from big meteorite impact. And this one is going to be happening even with smaller meteorites. Even if it's going to be bigger meteorites, of course, it can be just no Earth anymore, but yeah.
And what about if it falls?
I don't know exactly how big it should be for that.
Well, that's the thing. Like, we don't know. But will there be a difference if the meteorite would fall on the land over ocean? You would say?
I don't know. That would require a lot of experience in modeling how impact happen, and I would say that's more of a question for researcher who is doing exactly that. It's hard for me to speculate more than.
Okay.
I guess it's not obvious because, like, if it goes into the water, you'd get a tsunami. But if it goes on the land, it could cause an earthquakes, and earthquakes can also cause tsunamis. So it's like, would you get tsunamis either way?
I think tsunamis is one thing to be afraid of in both cases. I mean, stay away from the sea in that case, but we will not have a lot of time. Let's see. We have another question from Trikala, school in Greece, which is about the TRAPPIST system.
Mm-hmm. Let me just go back.
And if it has a habitable zone, like if you can have liquid water, I think that's what the people mean.
Yes. Okay.
And how if it shifts with time, like how is this thing? How is the habitable zone?
So the TRAPPIST system is very, very old. So we don't think the planets would move much. But the thing about very small stars, they're interesting. We're not quite sure if you could get planets on them. So the habitable zone is the distance away from a star where you have liquid water on the surface. So that's what we call the classical habitable zone. But there's also other factors of like how big the planet is and whether it has a magnetic field and stuff like that. But in simple terms, like our Earth is in the habitable zone of the sun, but so is technically Mars and Venus, and they're very uninhabitable. So that's why the term habitable zone is also questionable. So the thing about small stars like our sun, the habitable zone is very, very close to it. So I think there was actually some planets in it. But also when you get too close to the star, you get what we call tidally locked. So that's what's happening to the moon, where the moon is the same side of the moon is facing the Earth. So planets in the habitable zone of these very small stars, we think are tidally locked, and only one side is getting like light from the sun, the other side is in total darkness. So it's like, where would the water be, and where would life grow? Would it grow like in the Terminator between like the day and night side? And would the habitable zones shift? It might. So small stars, they're kind of like children having tantrums. Sometimes they're very calm, but then sometimes they just have these bursts of energy and want to destroy everything. So small stars are like that. They have these periods where they're just very quiet, and sometimes they just flare up. And those flares probably could shift the habitable zone a bit. And also, we think those flares could make it dangerous for life. So there's all these things where it's like, oh, it could be good or it could be bad. We're not sure.
Okay. Thank you. So just to rephrase what you said for the tidally locked planet. So in terms of liquid water, let's say, I mean, if this could be one of the habitability aspects, it's of course more than that. The fact of the tidally locked means that the planet would be too hot facing its star, too cold on the other side, and the hope is to have the edge, let's say, the edge between the two zones supporting some type of habitability, or if we could say at least some liquid water or some more constant, like let's say in between temperatures. I would say in between temperatures, and we leave it there because it's too many. Too many things. Okay, tidally locked planets, are very hardcore for life. You're right, because they are so hot on the side. Let's see. There was another question in the chat. And one question was, actually there was an impression of the students that they were amazed by the images about the formation of the stars, because they look, the images I think you showed from Hubble, I'm not sure, I think it was from Hubble.
Yeah, there was some Hubble and ALMA images.
And ALMA, yes. So yes, this one. I mean, it's also very impressive because the scientists use colors to show the different type of radiation. Is it right? Is it the color true? I mean, is it the color true? What would you say?
So with these ones, I don't think it is true colors. So with
microwaves or something like that.
Yeah. So this image is definitely not two color because it's looking in microwaves and radio waves. So we have to give it a color. This image is. So if you actually look at Orion through a telescope, you can see some dust, but it looks gray to our eyes. So this is also filtered to kind of make it prettier, but also draw attention to the important bits.
Okay, and the question then for that is, how easy or difficult is it to get these images?
Oh,
and if you collaborate with other scientists to make this happen?
Yeah, so generally, there's a few things you want. You want to have a big telescope, but also you want to have a lot of time. So you want to sort of just have the camera staring at this region for a long time to get the light to collect the photons. So it's hard to build images like this. I think they take, I'm not an observer, but talking to observers, you would spend like a whole night. So like 12 hours of nighttime and maybe only get like 6 images. So it takes like minutes to hours to get very high resolution images like this. Yeah.
Okay. And the scientists also have to apply for time, right? This is normally the case. There is one telescope, not one, there is limited number of telescopes and a lot of people want to use them. So
exactly. So you have to write very good proposals.
And to know where to look. Okay, that's great. I think we have covered all the questions of the chat. I don't know if there is something more from the YouTube channel here, because we covered the Zoom ones. Okay, so we don't have from the YouTube now. Most of the crowd is actually in Zoom this time. Yes, thank you very much for your time. In the case of the Q&A that is supposed to follow, which is in Russian, we'll wait a couple of minutes in case there is a school that understands this. And in the meantime, I want to to share my screen and show one other part of the EPSC Goes Live for Schools to communicate this to every teacher. Thanks, Rajika. So I'm sharing the screen here. Let me see. So we are, let me see if we can go here. Yes, just a second. So there is two parts of the EPSC Goes Live for Schools, and we see here today we have one more, two talks actually today. We had two talks in the live program from Rajika and Georgy. But there is also another part of the conference itself going live. So EPSC is the conference part, and
You said two talks from Rajika and Georgy. What?
No, you have made two talks today. I mean, it was a shared, but
okay.
It's two completely different expertise we had. So we had this is the live program, and the live program that we are supporting here with your talks is complemented by the on-demand program of EPSC. And what this is about, that was impressive because we had about 1,000 contributions in EPSC, 1,000 abstracts in this conference this year, even though it's virtual. And one every two agreed to make their talk available for education. This was an impressive response, first of all, because we had about 400 talks to choose from. And we curated and we made plain language summaries for about 12 of them. So we had to make a selection. And this is targeted to older age students, so high school and above, because we also have universities that are following this program. And they are connecting also to your topic. So the thematics that you showed today, which was the solar system, its versatility, as well as the exoplanetary part, is also connected with some more high level detail, I would say, scientifically, you know what I mean? It's not broken down for students as we did today, but intended for scientists to listen to. And those tend to be very complex. And that's why we thank you for helping us today to bring the general context to the kids. So we have put together plain language summaries for these talks. And there are a couple of talks which relate to other exoplanetary systems and to versatility in our solar system. So I invite you all to look at it. I'm going to put also the link there for the schools, even though they're going to get another notification per email that this program is live, and they can also look at this. And based on this input, on this coming Friday, we're going to have the last live talks. And one of these is going to be an analysis of a scientific talk. So we're going to choose one of those, and we're going to present what is the general language of the scientists. How do they use hypotheses? How do they use errors? Why do they talk with probabilities? And when do they choose to use a model or an observation? So that's part of this program here. I'm going to stop sharing. So there has been, yes, there has been very good comments coming. You can read them all, I think, in the Zoom from a teacher in Turkey who has been following us, and they are very happy. So actually, I'm thanking you for joining us, and that you support this effort. As far as I see here, we don't have any school that can follow the Russian Q&A. So I want to invite here Anastasia, who is a co-host, and she speaks the Russian language.
I'm here.
Hi, Anastasia.
Hi.
Hi. So, yes, I would like to say, just for the sake, because this is going to be recorded, we can also answer one question that was posed from Georgy, from who speaks the Russian language, and we answer it also. We ask it and answer it in Russian, so that we also have a part for the people that are going to look at it later, the recorded part. Is it okay with you, Anastasia?
Yes. Which question?
Well, the question, I think the question we can go with is about the dust, which was relevant to the topic and research topic of Georgy. How do we get information for the dust around other stars? What do we know about it?
Я переведу, да, как мы получаем информацию о пыли, да, вокруг звезд, и как мы собираем ее.
Which language should I answer in?
Nasia, it's about dust, how we
Russian.
collect the information about dust, right?
Yes, you should answer in Russian, and we get a bit of input. Thank you.
Дело в том, что я в смысле, тут есть два основных направления. Первое — это изучать пыль, которая у нас в метеоритах, и этим я занимаюсь, и про это я могу немножко сказать. А другое дело — изучать пыль вокруг звезд и что-то такого типа. И про это я плохо знаю, и я так понимаю, вопрос именно про это. Вот. Ну, то есть глобально я знаю, что это можно как-то наблюдать телескопы и изучать пыль вокруг звезд.
А метеоритную расскажешь?
Да, в метеоритах для изучения пыли, досолнечной пыли, для этого необходимо... эта пыль всегда отличается огромными изотопными аномалиями, и для того, чтобы... То есть для ее изучения есть два основных способа. Первый — это использовать такой прибор, как ионный зонд, и он позволяет делать изображение изотопного состава. И если мы видим что-то очень аномальное, это, скорее всего, досолнечное зерно, которое прилетело с другой звезды. И второй вариант найти такие зерна — это растворить много-много-много-много-много метеорита, и тогда часто оказывается, что самая туго растворимая часть, если растворять метеорит в кислоте, то то, что не растворилось, часто тоже досолнечное. Вот, это два основных варианта, как их найти. Это отвечает на вопрос?
Да, спасибо. Nasia, I think we have answered it in Russian.
Yes, I could follow two words.
Would you like us to have another question in Russian, or?
Yes, I think from the ones that were posed on the expertise of, I mean, Georgy can also translate what he heard also from Rajika, like the part of the stars, because I think we are all in the same page here. So one more question is for the TRAPPIST system. This would be a nice one to make to Georgy. So for the TRAPPIST system, the question would be, how is the TRAPPIST system different from ours? And how do we define habitability there? Like, what would we look for it? Can you answer this?
You answer in Russian, right?
You will also be asked in Russian by Anastasia. Thank you.
Okay, Rajika, maybe can you answer and I will translate?
Yes, I will.
You make a challenge for us.
I make it a challenge. I am aware. So let's not make it complex. We can ask, how do we define the habitable zone in TRAPPIST, if we can at all?
Okay. The habitable zone around TRAPPIST or any star is the distance that a planet has to be to have liquid water on the surface.
Определение обитаемой зоны, согласно Раджике, это расстояние, это если планета находится на таком расстоянии от звезды, что на этой планете есть жидкая вода. То есть недостаточно далеко, чтобы было слишком газа, слишком газообразно, не испарялась вода, и недостаточно близко, недостаточно далеко, чтобы было холодно и лед. Отлично, мне переводчик. Yes, you can continue if you want.
Yeah.
Oh, okay, good.
So for our, I guess we'll leave it there then. Yeah.
We can leave it there. I think the habitability already in Russian is something. Thank you. The challenge, I think you went very well for the time we had to prepare this. Thank you all. So yes, I think we can close here with both Q&As. And it was a pleasure to have you here early morning. And it was a pleasure that you joined for this 1 hour and a half almost.
It's okay.
We had 5 countries, schools from 5 countries following this today, and we're looking forward to also like the final events of this week. And thank you, and we're looking forward to see you soon. Anything you have to tell us about what you liked or what you would like to correct for next time, we're here, and we're here to listen.
Thank you.
Thank you.
Thank you very much.
Thank you. Спасибо большое.
Спасибо. Thank you.